Hi, my name is Ian Fogarty, and I'd like to talk to you today about organic molecules and how their polarity impacts the solubility. In grade 11 chemistry, you would have talked about solubility, and you would have gone through a rule that says like dissolves like. That means that polar things like to dissolve other polar things, and nonpolar things like to dissolve other nonpolar things. In order to make sense of this, we need to look back at electronegativity. So we're going to use the Pauling scale. So electronegativity on the Pauling scale for carbon is 2.5, and for hydrogen is 2.1. The electrons in this bond right here spend slightly more time around the carbon than the hydrogen, but they're so close in electronegativity that it's not very perceptible, and so a CH bond is considered a nonpolar bond. They are shared pretty much equally. Electronegativity of oxygen, however, is 3.5 and 2.1. So that is a significant difference, and the electrons in this bond spend more time around the oxygen than around the hydrogen. That leaves the oxygen with a partial negative charge and a partial positive charge on the hydrogen. The same thing happens with nitrogen. Nitrogen has electronegativity of 3.0 compared to 2.1. That makes a nitrogen-hydrogen bond polar. Electrons spending more time around the nitrogen than around the hydrogen, a slightly negative charge and a slightly positive charge. Here we have a sodium chloride molecule, and it's an ionic compound, and we're very familiar with the fact that sodium chloride dissolves very well in water. This is a great example of polar dissolves polar. Hydrophilic means that these things like to be around water, loving of water. When this dissolves in water, you end up with sodium with a positive charge, and your oxygen, because it's the electronegativity of oxygen is 3.5. and hydrogen is 2.1. That makes the slightly negative charge on the oxygen, and a slight positive charge on the hydrogen. And so the oxygens will point themselves inwards. There's going to be attraction between the positive of the sodium and the partial negative charge on the oxygen. So you end up with a sodium with a solvation sphere. And we'll look at that more in detail when we talk about enthalpy. The chlorine will have a similar situation, but the hydrogens would be pointing inwards now because their partial positive charge will be attracted to the negative charge of chlorine. And so something sodium chloride, ionic, will dissolve nicely into water. Ionic is a very extreme form of polar. Water is a polar molecule, and so water will dissolve sodium chloride. Here we have some octane and some more octanes, and we have 3 butanes over here. So these are going to be full of carbon-carbon bonds, which are nonpolar, and carbon-hydrogen bonds that we didn't show that are also nonpolar. So this is going to be a nonpolar molecule attached to another nonpolar molecule. And so we have these London dispersion forces, or van der Waals forces, that sit in between there, holding these things together like that. Butane can come and stack in there quite nicely without disrupting the van der Waals forces too much. And so this whole thing of nonpolar dissolving nonpolar, butane is nonpolar, octane is nonpolar, so nonpolar dissolve nonpolar. They are hydrophobic. They do not like water. Sometimes we use slang, we call them greasy. So look how these ideas of hydrophobic and hydrophilic impact the solubility of alcohols. Let's start off with methanol. So in methanol, we have these carbon-hydrogen bonds. So these areas are going to be non-polar. Electronegativity of hydrogen is 2.1 and carbon is 2.5. That's pretty much equally shared. So it's going to be a non-polar, all those non-polar bonds. Whereas electronegativity of oxygen is 3.5 and hydrogen is 2.1. So the electrons that are in this bond are going to spend more time around the oxygen. It's going to be a partial negative on the oxygen and a partial positive on the hydrogen, and this is going to make for a polar end here. So we have is a molecule that's confused. One side of it is polar or hydrophilic, and the other side is nonpolar or hydrophobic. If you take a little bit of methanol and you throw it into some water, what's going to happen? Part of the molecule wants to dissolve in water and the other part doesn't. And the answer to the question is it dissolves very nicely in water. You have a nice attraction here, and it dissolves very well in water. The polar voice is a lot stronger than the nonpolar voice. And in ethanol, we have a larger nonpolar group and still the same small OH polar group. Water is going to be attracted to this end and not to the nonpolar. And what's to happen? Well, ethanol dissolves completely into water too. So again, the OH wins. So we're gradually increasing the nonpolar side of things by going to propanol and this small little OH group. So we have 3 carbons and the hydrogens around for the nonpolar side, the hydrophobic side, and we've got a 1 polar group, the hydrophilic side, slightly soluble, slightly miscible. Finally, the nonpolar side of the molecule is getting its way, its voice is loud enough. When you get to butanol, the carbons are far outweigh the polar OH group, and so this is insoluble in water. So the longer chain means that the non-polar voice becomes stronger and the OH group is forced to not go into solution. But these situations are kind of close, where the non-polar side doesn't really want to go in water but could be convinced, and the polar side down here really would like to be in water but could be convinced to not go. And so there's not a big conflict between these two. There's not a lot of extreme. Now what would happen if you made a soap where you made something that the polar end of things was very polar and really wanted to be in the water and was going to fight hard to be in the water? And what would happen if the greasy non-polar hydrophobic piece was very greasy and very hydrophobic and really did not want to be in water? What happens when you take this soap that has one end that really wants to be in the water and the other end that really does not want to be, and each end is very adamant about where it wants to be? You can end up forming this little film along the top surface of the water. So that way the polar head groups can be attached to the water where it wants to be, and they stick their greasy hydrophobic tails up in the water, in the air, and you end up with a soap film. And we've all seen the soap dish detergent commercials where the grease is on the water and then they add a little bit of soap and it pushes it to the outside. With a little bit of work, you can convince the soap to become embedded in itself, and so you can end up with something like this, where that's going to be a problem because you have the polar head group which is happy inside the water, but this greasy tail is not. So one molecule by itself is probably not a good idea, but if you have a whole bunch of them, if a whole bunch of these soap molecules get embedded in the water together, they can point their greasy tails towards each other and keep their polar head groups on the outside. And so the polar head groups are attached to water, which is good. And then their greasy hydrophobic tails are together with each other, which are also hydrophobic and greasy. And then everybody is happy. Like dissolves like, and like dissolves like. If we have a little grease on our glassware, just adding water is going to make it hard to get rid of. So if we put some soap and turn it into a micelle, then the micelle can come down and you can use some elbow grease and deform that micelle, and the grease will become like dissolves like, and so we'll end up with this nice grease dissolved in the greasy hydrophobic tail part of the micelle. It will all be trapped together, and down the drain your grease goes. Now, with a little bit more time and energy and effort, a lot more shaking, often some freeze-thaw activity, you can form something called a liposome, which looks something like this. So we could form something like this, where we have the polar head groups all turn their heads inwards, and so they would be happy because you'd have water inside, which is polar, and then you have the polar head groups all together, which are polar. The only problem with that is then you have these greasy hydrophobic tails that are extending out into the water, and that's not a good idea. However, we can start adding some more soap bubbles out here, Where now this guy is going to be pretty happy because the polar head group is facing the water and its greasy tail is in between two other greasy tails. And so that's going to be pretty good. And if I continue doing that, where you have water on the inside and it's connected to the polar hydrophilic sections, that's great. You have this other section here where it's greasy tails on greasy tails, and so you have this hydrophobic and hydrophobic interactions, and so like dissolves like, and they're happy. And then on the outside you have the polar head groups again, where you have all the water, and so it's like dissolves like again. And this is called a liposome. So you have a film of water on the surface, you have a micelle, and then down here you have a liposome. Now liposomes are very useful. They use them a lot in pharmacology. Is you can put different kinds of drugs in here and they will protect them from the outside world. They will sometimes fall into different areas of the blood, like in cancers and things like that, and they will gradually leak out. So it's kind of a way of time delaying it. So they gradually leak out and then can be useful to the cell. So we use liposomes a lot in pharmacy. Now here we have a phospholipid, and so you have a polar head group, this is the blue thing, and so we have a phosphate, it's very highly polar, and then you've got another O bonds in here, this whole thing is very polar, and you've got these long chains of carbons, C's and H's. This one's got a double bond in it, happens to be a cis double bond, and so what it does is it puts a little kink in that tail. So we often kind of show it like this. We have a polar head group and then these long hydrophobic greasy chains, and then the double bond in here puts a little kink in it and bends out the tail sideways. And this would be a phospholipid. So this is similar to soaps, except for now it has two tails instead of one. Well, if you put this in water, you get all the same things. You can get a film, you can get a micelle, but you can also get a liposome. Here's an example of our liposome where we take our phospholipid and we put their heads in forward so that you have your water in here and their greasy tails on the outside, and then their polar head groups on the outside. And so this would be a phospholipid bilayer, one layer on the inside, one layer on the outside. And this is the model that we use for cellular membranes, because you can put your nucleus in here and the inside cell of your contents, your mitochondria, and all those kinds of things inside here. This is a membrane of a cell. Now in some of your amino acid chains, you had some molecules, some side groups that were polar and some that were nonpolar. And so if you had some that were polar, like this end, and some that were nonpolar, you could take a protein like this, and where would it sit? It could sit right in here in the cell. And that way the nonpolar groups would be happy in this nonpolar section of the membrane, and this polar part would be happy, this hydrophilic part would be happy. It would be sitting out into the plasma or into the cytoplasm, and so it could grab things that comes by or something like that. The one problem with this is that it could fall out, and so maybe what you want to do is have a protein that looks more like this, where it has a non-polar part with two polar parts, and that way it could sit in somewhere like that, and the polar end here is attached to the polar, non-polar with non-polar, and polar out in the center, and that way it's kind of an anchor. So you can't really pull it out very easily, because that would mean that the polar in part would have to go through the membrane, and that's going to be a little more challenging, so it kind of anchors it. Maybe you could have a protein that when it is all put together, it makes this kind of shape. It makes this kind of a shape where it's got some polar mostly around the ring, and another polar around the ring, and then mostly non-polar in the center. And so if that were to go into the membrane, it could perhaps fit in something like that. And now you would have a tube. And in that tube, maybe you end up taking potassium or hydrogen pumps and chloride pumps, sodium pumps, and now you can pump things in and out of the cell. So this polarity idea is really important for the way that our whole body works, the way our cells work. It depends on how our membranes are formed. It shows us where our proteins are going to go. It shows us how things can be dissolved. It's absolutely very crucial. Thank you very much for your time.